Hello friends, today we learn equilibrium of a body and example of that. So you can find out a complete detailed lecture on equilibrium of a body in a previous lecture series. So here we start with fundamental concept, what is requirement of a solution for the equilibrium of a body example. So first of all, we learn in previous lectures that is a Lamys theorem. So that you required to know what is Lamys theorem. That is very much helpful to solve the example of equilibrium of body. Second thing is to draw a free body diagram, that you also required to know. So for that we just take a look at to the Lamys theorem. So it is state that if three coplanar forces that is acting at a point and that is in equilibrium, so then each force is proportional to the sine of the angle between the other two. So that required to take into the mind, and Lamys theorem is very much helpful when there are three coplanar forces are acting at a point. So here we have a force P, Q and R, and these all forces are coplanar forces, and in between that forces alpha, beta and the gamma are the angle. So to resolve that we require to know a single force, either P, Q or R, and any angle if you know, so you can easily find out other two forces by using the equation of Lamys theorem. This is also known as a sine rule equation. So you can find out other forces, that is you can say that unknown forces in the force system. Now on free body diagram, another lecture you can find out in previous lectures how to draw free body diagram and how to understand the requirement of our problem. So here one string is given and this is the weight of any body, so that is particularly in downward direction, so that we require to draw in this form, and what are the tension that is available on that string, that is required to find out. So these are our three forces that is required to resolve in this system. Further, if we see definition of that, so that is nothing but a free body diagram is a sketch of an object of interest. That means whatever the requirement of your problem, that is known as a object of interest, that you require to again draw with a free body diagram, and surrounding object that is not required, that you leave, and you can show a complete and easy diagram to resolve the forces. In other way, if we see free body diagram, that is important step in the solving the mechanics problem, since it helps to visualize all the forces acting on a single object. So that is nothing but a conversion from a realistic problem to the simple form. So let us see some example how to do that, so you can understand here in very clear manner. So here there is some human body that is available on this string. So the string has some tension available in form of T1, T2 and T3. So these are the main three forces that we require to solve. So these are of our interest. Also we have some reaction in particular direction of the forces. So this is a final and very easy conversion of this real problem to the free body diagram here. Second, if we see that sphere is attached with some chain to the wall, so here due to the weight of that sphere, what is the reaction that is generated with this wall? that is of our interest, that you require to draw with proper direction, and what is the tension available in this chain. So these are our basic three forces that is converted like this in free body diagram. So you can very easily solve this. So I think it is clear now how to draw a free body diagram of a real problem. Further, if we see when a block is on a ram, so how to give the proper reaction and the forces in the particular direction, and you can resolve in the free body diagram like this. Yeah, you can take a one real problem example of cantilever beam also. So here some weight is available. So due to that weight, what are the reaction moment that is available on that beam? You can also convert that real problem into this free body diagram like this. So now this is a free body diagram, so you can easily resolve it by putting the main requirement of that problem as it is, and the further thing we are not required, so we leave it, and conversion of that into a free body diagram, that will make a easy analysis for the problem. Now look at to the example of equilibrium now. Let us take example number 1. So in this example, a sphere of weight that is of 100 Newton and diameter of 20 centimeter is tied with a smooth wall by string. So this is a given problem available, and that is with some height from the center of that sphere to the where the string or chain is tied, so that is 2 meter, that is given already. Now we require to find out a tension in a string and a reaction from the wall. So in this problem we have two things that is of important. So one is this T, that is the tension, and second one is the reaction from the wall, and this weight is already given in the problem. So we know that weight is in downward direction, reaction that is coming from the wall in this particular direction, and the tension in chain that is in this direction. So we can easily plot a free body diagram of that like this, and we can just take a part of that is of our interest. So this is the part where we are interested to resolve the forces. So again we draw in a particular manner. So now these are the three forces, and this is a point where those forces are acting. So this is our problem now, and to resolve that problem we have to first look at to the angle between that forces that we require to resolve as per the requirement of Lamys theorem. So again here this is 2 meter given, then from that 2 meter if you find out that angle, and again this is the dimension radius of that sphere, so 0.2 meter is given as a diameter of this sphere, so that is 0.1 meter is given here. So two side you know very well, this one and this one, so you can easily find out this angle by applying tan over here, that is 87.14 degree. So now we have this is the resolution of angle TOB, that is 87.14 degree. So after resolution of that angle we have a complete figure like this. So from that angle you can resolve another angle. So this angle is 90, so you can find out this complete angle. So that is 90 plus 87.14, so that is 177.14. so here you can make a sign of plus, okay, not minus, that is a plus. And second thing is that if this is the angle of 87.14 and this is complete horizontal line, so with that you can find out this angle, right? So that angle is 180 minus this much, so that is 92.86 degree here, and this make a perpendicular to each other, so that is 90 degree completely. So out of that angle, now it is very easy to resolve these forces. Now apply a Lamys theorem here. So one force and the opposite angle you can use, so T divided by sine 90 here, and you can use RW, that is the reaction from the wall. So angle is 177, and the W is the force, the angle is 92.86. Now you can resolve it one by one. So this is the full equation of Lamys theorem. You can put your one value of the force, that is 100 Newton, that is given in form of the weight of that sphere. You can resolve first part, that is T and 101. So come out with the answer. The tension in string, that is 100.125 Newton here. You can resolve it by the mathematical operation. Again, second, you use this RW and this part, so the answer would be the 5 Newton, that is the reaction of a wall. So I think it is clear how to solve the different force values from the Lamys theorem. Now let us take a second example. In this total 3 cylinders are given, that is L, M and N, and the weight of those 3 is 100 Newton each, and 100 mm is the diameter that is placed in a channel of 220 mm. So one dimension is also given. So we require to find out first the cylinder L on M at the point of contact. Okay, so what is the pressure between this L and M? Second is, what is the reaction at the base of cylinder M, and what is the reaction on cylinder M from the wall. So look at to the figure completely. So 220 mm is the size of this container, we can say, and L, M and N are the cylinder, and that is available in this pattern. So first thing is we require to find out the force in between L and M. Second is what is the reaction from the base, and third one is what is the reaction from the wall on M. So for that, first we resolve the dimension. So here 220 is the overall dimension, so 110 mm, that is a dimension given here. So I think this has some gap available in between these two. So overall dimension is 50, and you can say this is a 60, and that is the center of this. Here there is no gap available, so from that you can easily resolve. This is a complete diameter, half of the portion here and half of the portion here, so that is 100 mm. Now after that we take a complete pattern of these three, and 60 is the dimension here, 100 is the weight of each sphere here. So if we can take that, what is the RW, that is the reaction of the wall, RB is another force, that is from base of that container. Now you can resolve that in particular manner. So before that we can also resolve from the dimension 60, and another dimension is 100 mm. So you can find out this theta, that is come out 53.13 degree. Now for the resolution we can separate out this thing into a part. So first we start with first portion. So we require to resolve this part using a Lamys theorem here, and for that we have 100 Newton, this RLM and RLN, that is the forces. And if we see that this is the angle 53.13 degree, so by using angle rule we can say that this theta as well as this theta is similar than that. So let us resolve that using this free body diagram and applying that. So here that is a 90 degree, that is completely perpendicular, and here if we remove that 53.13 from both the sides, so this angle is 180 minus 2 times 53.13 degree. So I think it is clear now. Apply Lamys theorem using this two forces RLM and 100 Newton. So we can come out with this result. RLM is equal to 62.50. Now we only required a force in this sphere that is available this side, so we are not going to solve this side right now. So for that we come out with one answer, that is of RLM, and that we carry forward in next figure. So RLM is available, and this is a free body diagram of this sphere. Now in this we have total 4 number of forces: RLM, 100 Newton, RW and RB. But if you see that the requirement of Lamys theorem, that is only 3 coplanar forces, then you can solve that. But here 4 forces are there, so you can solve that by using equilibrium condition. So you can resolve the horizontal forces and the vertical forces by using a method that is called static equilibrium methods, and you can find out required answer in form of RW, that is the reaction from the wall, and the RB, that is the reaction from the base. So this is the final answer. What is the requirement of the problem 1, 2 and 3. So it is clear now how to resolve the forces if the example of this type of sphere is available. Third example, if we take here a smooth sphere is given, radius of 150 mm, weight of 250 Newton, that is rest on horizontal channel having a vertical walls. The distance is also given, that is 560 mm, and we require to find out the reaction at point A, B, C and D. So look at to that, this is the A, B, C and D. So this is the reaction from the wall on this sphere. This is in between spheres, that is B. C is the reaction from the base and D is the reaction from the wall. That is required to find out here. For that again you require to resolve. 560 is the dimension. So you can start with half the portion of that, that is 260. 150 is again radius of that spheres, so you can easily find out this alpha angle here. So alpha angle, if you require to find out, you can put a mathematical equation and find out alpha is equal to 29.92 degree here. Again you can separate out the figure in this way and start with given problem in a proper manner. So for the solution of that, we first write this. So here RA, RB and 250 are the forces and one angle is given. Another angle you can find out very easily, because this is a 90, this is also 90 and this one is also 90. So you can resolve that in proper manner and apply a Lamys theorem like this. 250 is the known force here, so by using 1 by 1 term you can resolve. RA is 434.32 Newton and RB is 501.11 Newton. Now RB is available here, so you can now replace that RB to solve this free body diagram. Again we have 4 number of forces available here, so again apply a equilibrium condition and come out with this answer. So if we resolve that in X, so we have RD and the component of this RB in this particular direction, so you can resolve that two forces, so we can come out with RD is equal to 434.32 Newton. Again, there are two forces, 250 and RC, that is available, and third one is the component of RB in this particular direction. So you can solve that and come out with RC is equal to 500 Newton. I think it is clear now. Example number 4, if we take, so that is 100 Newton weight is suspended by two wires as shown in figure. So here two wire, that is in orange color and the blue color, and 100 Newton is the weight given. Also length of that wires as well as the distance where it is attached, that is also given in form of 5.7 meter. So again we know that, yeah, this is given, this is 90 degree is given, that is perpendicular to each other, and we require to find out alpha and beta. So of our interest, this is the complete portion that is of our interest, and we require to find out that. So first of all, we find out what is the angle alpha. So distances are known, so you can easily find out that alpha by using 3.5 by 4.5, applying a 10, that is 0.777. So alpha is come out to be a 37.84 degree. And also find out the tan beta is equal to 4.5 by 3.5, so beta is equal to 52.12 degree. Now angle is available. Now resolve that angle in a required portion. So here this is the angle given, so by rule of angle, this is also 37.84, and again this is also 52.12. so this is of our interested area, where we require to apply a Lamys theorem and find out the value of this T1 as well as T2. So now it is very easy, I think. So write down this in this form of Lamys theorem and apply one by one. So first of all, you can put the values of this sine angles. So this is in a simple form now. Now resolve that one by one. So we have T1 is equal to 30.5 Newton and T2 is equal to 39 Newton. So this is the requirement of the problem. If we go further for a last example, so weight W is suspended as shown in figure like this. So this weight is again unknown. This weight is given as 100 kilonewton. And the angles are also available like this, 60, 60, 45, and this is of 30 degree. So let us try to solve that. So for that, we first resolve this part that is of our interest right now. So 100 kilonewton is given as again a rule of angle, this degree, if we say that is of 30, this is of 60. Now let us resolve that by using Lamys theorem. So you can very easily resolve it now. So R3 is 86.6 kilonewton and R2 is 50 kilonewton. So R2 is now available, that is the tension in this blue string, and R3 is also available. So these answers are available now. If we go further in a second part, so free body diagram of second part is this. W is unknown, R2 we know that is 50 Newton, and R1 is also unknown. Now again we resolve that angle, so this is 45, this is 30, and we go for the resolution. Again we just sort out a different angle. What you know, this is also, we can say 45 degree, this is 90 degree, and this is also 90 minus 30. So you can apply properly angle and write down in form of Lamys theorem. Solve one by one, you can get W is equal to 18.25 kilonewton and R1 is as 61.24 kilonewton here. So I think it is clear how to resolve an example of equilibrium of a body using Lamys theorem.